Welcome to this explainer. Now, if you've been anywhere on the internet lately, you've probably seen those viral clips of 3D printed houses going up in a matter of days. It's fascinating, right? But today, we're going to move way past that superficial wow factor. We're diving deep into the highly orchestrated symphony of hard science, advanced software, and heavy robotics that actually makes 3D concrete printing work. Because trust me, it's not just a giant hot glue gun for cement. It is a meticulously engineered process from start to finish.
So here is our roadmap for today. We'll kick things off at the conceptual stage with digital design and BIM. Then we'll see exactly how that data gets sliced for the robots. After that, we'll explore the incredible world of second-generation smart printers, take a really close look at chemical acceleration, and finally step right into the next era, Construction 4.0. All right, part 1, digital design and BIM, the brains of the operation. This is where we establish exactly how these digital models are prepped long before a printer even gets powered on.
You see, you can't just hand an industrial robot a rough sketch and expect a house. Building information modeling, or BIM, has to integrate directly with computer-aided manufacturing systems. This software combo calculates a mathematically perfect route for the printer. It dictates the bead geometry, which is just a fancy way of saying the exact shape of the extruded concrete, along with the precise speed the nozzle needs to travel and the absolute perfect timing required between laying down each layer. To keep it simple, the whole shebang really breaks down into 3 major stages. First up is data preparation, where all that complex toolpathing and digital slicing happens. Second is material preparation, where the concrete is expertly mixed and pumped. And third is the actual component printing, featuring the extrusion and layer stacking. It's this incredibly seamless flow from a purely digital blueprint to physical reality. Which brings us to part 2, data slicing and toolpaths, mapping the robot's route. Now that the software has a plan, let's see how the hardware takes over for a hypercritical phase of the operation. Translating a digital 3D shape into physical, real-world movement is tricky. Traditionally, systems use what's called the sequential layer method. Think of this like cutting a loaf of bread into flat, equal slices. It works, sure, but it can sometimes leave these weak geometric gaps between layers, especially if you're trying to print complex curves. The much more advanced approach is the tangential continuity method. Imagine a sculptor smoothly varying the thickness of their clay in 3 dimensions. This method creates constant contact surfaces between the printed layers, completely avoiding those structural weak points. But to actually pull off those complex, tangential toolpaths, you need some seriously heavy-duty hardware. We're talking about a 6-axis industrial robot. This goes way beyond your standard, simpler gantry systems that usually just move in basic X, Y, and Z directions. A 6-axis robotic arm offers incredible, extra degrees of freedom to the printing nozzle. That flexibility is exactly what allows for those highly accurate, locally varying thicknesses in the print that we just talked about. Moving right along to part 3, second-generation smart printers, the all-seeing eye. Let's step into the problem-solving phase here, because early 3D printers were essentially blind. They just followed instructions and basically hoped the concrete behaved. Well, not anymore. There is a really defining quote that sums this shift up perfectly. A second generation of construction 3D printing platforms is emerging. Combine additive manufacturing with complementary operations using robotic automation, sensors, and artificial intelligence. This is a massive, game-changing leap forward. By bringing AI and smart sensors directly into the mix, these second-generation platforms solve historical limitations, like weak layer bonding or suddenly collapsing structures, because they can actually adapt to what's happening on the construction site in real time. So how exactly are they pulling this off? Through closed-loop control systems. These setups use machine vision cameras and inline computer vision to actively watch the extrusion process as it's happening. If the bead geometry is even slightly off, or a tiny gap starts to form, the system immediately triggers on-the-fly defect mitigation. By using AI for predictive process control, the machine course-corrects instantly, long before a minor flaw ever gets the chance to become a structural failure. It's literally a 3D printer that actively supervises its own work. All right, part 4, in-nozzle chemical acceleration, chemistry on the fly. We've covered the digital brain and the robotic arm, but now let's transition to the physical blood of the operation. This is all about doing advanced chemistry on the fly to literally defy gravity. Here's the challenge. In a standard layered extrusion, building up too fast means the wet concrete at the bottom will inevitably squish under the immense weight of the layers on top.
It severely limits how quickly you can build. But if you want to achieve a complex, rapidly stacked structure that holds its shape perfectly, you have to add chemical accelerators like calcium aluminate cement slurries directly into the nozzle right as the concrete is being pushed out. This dynamic chemistry allows the fresh concrete to harden and hold immense weight almost instantaneously. And the results, honestly, they are staggering. Thanks to those in-nozzle accelerators, we can hit vertical buildup rates of 2 to 6 meters per hour for localized structural elements, like columns. To put that into perspective for you, printing a large perimeter for a standard full house normally builds up at a pretty sluggish 0.3 to 0.5 meters per hour. This rapid stiffening chemistry is the secret sauce that makes printing towering elements possible without them just collapsing into a giant puddle of wet cement. Finally, Part 5, entering Construction 4.0. The next era. All of these breakthroughs, the complex digital modeling, the AI-driven smart sensors, the real-time dynamic chemistry, they are all culminating into something much, much larger for the entire industry. It is truly awe-inspiring to step back and look at how incredibly fast we got here. Back in 2004, researchers were really just testing basic feasibility with early contour crafting prototypes. Fast forward to 2016, and we saw massive gantry systems capable of printing perimeters for full-scale houses. And now, today, we are looking at fully certified AI-driven smart printers that even handle automated finishing. The technology has matured from this fragile experimental concept into a highly robust, undeniable industrial standard. And if you're wondering why this matters in the real world, let's look at India's first 3D printed post office, built by L&T Construction. A conventional construction workflow for this exact building would have taken 8 long months to complete. The 3D concrete printing method executed the whole thing from start to finish in just 43 days. And the overall cost? A massive 40% cheaper. This perfectly proves how the highly complex technical workflow we've been discussing translates directly into undeniable real-world savings. So, the big question we are left with is this. With AI continuously monitoring structural quality, 6-axis robotic arms executing mathematically perfect toolpaths, and dynamic chemistry accelerating structural strength on the fly, are we looking at the end of traditional construction as we know it? It certainly seems like the blueprint to reality has been forever rewritten. Thank you so much for joining me on this explainer. I hope this deep dive into the technical workflow of 3D concrete printing sparked your curiosity, and I highly encourage you to keep exploring the fascinating, rapidly changing world of Construction 4.0.